You see this point on my map? It is actually right on my lawn. But if I try to navigate to it using my phone's GPS, then I will never hit it. And that is the biggest weakness of GPS. It is great at finding your next home improvement store, but bad at finding exact spots. But such precision tasks do matter though. Like for example when landing a drone, for lawnmower robots, or for electric vehicles finding the sweet spot for inductive charging. And I know this last example sounds a bit random, but it was actually part of my bachelor thesis 11 years ago. Now back then, and still nowadays, the solution to this problem is RTK GPS, that offers centimeter levels of precision. Back then though, the available modules were not ideal, and thus I achieved pretty terrible results. But times have changed, and nowadays even your lawnmower comes with RTK GPS. And that got me wondering how easy and cheap it is to use this technology nowadays for your own projects. So in this video, let me not only show you how bad GPS really is, but also find out whether RTK GPS is now easy and affordable for DIY projects. Let's get started! As devices get smaller and smarter, today's hardware demands electronics that can bend and fit anywhere. And that is where my sponsor JLCPCB comes into play, who offer advanced 1 to 4 layer flex PCBs starting at just $2. Crazy! They exclusively use fully adhesive-free base material for maximum reliability, featuring 85% light transmittance, 200C heat resistance, and full SMT assembly support. You get exceptional boards, precision tailored to any custom shape or size. And to make this even more tempting, you can now bring your FPC ideas to life through the OSHWLab Stars 2026 contest. They're offering an $85,000 cash prize pool, material and shipping support. So click the link below to join today. Now first off, we need a proper test setup, because I don't want to become the human robot for this. So I got myself this promising looking metal tank robot kit that looks like it should be able to handle my lawn. So after putting the wheels together along with the main chassis that houses the battery and motors, I was pretty much done here within around 30 minutes. And I know it comes with way more accessories and sensors that we could add, but I wanted to keep it basic and also use my own stuff. Except of course the battery and motors, because with its nominal voltage of around 7.4 volts, it is a perfect fit for powering the motors. So let's have a look at the remaining mandatory hardware for basic tests. And for that, I will be using an ESP32 microcontroller, a power converter board, and 2 overpowered motor drivers. Now these BTS 7960 are advertised for 43 amps, so a total overkill for our motors. And in case you're wondering, the power board will convert our raw battery voltage into lovely 5 volts for pretty much all of our electronics boards. And with the basics out of the way, I mounted my 4 boards in pretty much the most crude way possible, using lots and lots of double-sided tape, which worked out better than I initially expected. As soon as that was done, I then did all the wiring according to this wiring diagram that you can download along with all other information using the link in the video description below. And for the final step, it was time for programming. And the code I created here basically only creates an access point that I can log into via Wi-Fi. And when I visit the ESP's IP address, I can see this web remote that allows me to adjust the overall speed of the tank and in which direction it should move. And as you can see, after powering everything up, it worked pretty great on my workbench and also on my lawn. Except maybe the turn right and left function. But besides that, it was now time to find out how bad normal GPS really is. For that though, I didn't get myself a bottom-of-the-barrel GPS board. Instead I got myself this M5 stack GNSS module, because it is built around a u-blox Neo M59 receiver that comes with some pretty great specs, but it is also a bit pricey. So to mount it, I built myself a small tower on my robot using standoffs and a piece of MDF. There I firstly secured the GPS module, followed by the antenna, and then I wired the module up to the ESP32. Last but not least, I also added this B&O 085 board to my setup, which can do a lot of things, but simplified speaking, it is for orientation. This will be helpful, because the GPS tells us where the target is, but the robot also needs to know which direction it is currently facing. And with the GPS test hardware complete, I turned on the battery and was happy that nothing exploded. That means it was time to extend the code, so that it shows me not only the current GPS position, but I can also save it in a slot, and then once the robot has another position, navigate to it by pushing a button. And you might also have noticed that there's a calibration section in the UI, which is for the orientation board, and that honestly cost me lots of troubleshooting before anything worked properly. But eventually it worked, and firstly you can see that we got a valid GPS position, which I of course had to censor throughout this entire video for obvious reasons. But anyway, for my proper GPS test, I marked my saved starting point and simply let the robot drive to it from any direction and position on my lawn. And as you can see, that kind of worked pretty well. I of course marked where my robot landed, and you don't have to be an expert to see that there was a huge inaccuracy. When we bring out my 2-meter tape measure and look at it all from above, then a tolerance of 2 meters is no problem when it comes to normal GPS. And truth be told, we didn't need this robot driving experiment for that, because when we save a GPS point and not move the robot, we can see how hard its position is drifting away, even though it is standing still. This inaccuracy happens because a GPS receiver basically calculates its position by measuring its distance to several satellites in orbit. And it does that by using time differences. For example, satellite A sends out a signal at time X, and the receiver gets it at time Y. This time difference, multiplied by the speed of light, tells us the distance to that satellite. And by doing this with several satellites, usually at least 4, the receiver can calculate its position on Earth. The problem is that these timing measurements have to be insanely precise, because even a 10 nanosecond timing error already equals around 3 meters of distance error. And such errors can be caused by a lot of different things that constantly change and that we cannot really control. So let's get rid of this normal GPS stuff and let's switch over to this RTK GPS kit that sadly still nowadays costs a little fortune. But I wouldn't call it overpriced, because the main module this is all built around, the u-blox ZED F9P, is simply not a cheap module. And we need 2 of these, along with 2 antennas and a way to let the 2 stations talk to one another. Because, as you might already have guessed at this point, just like with my robot lawnmower, we don't need 1 GPS receiver, but 2. One will be moving while the other one is stationary. This way, the stationary one can compare its GPS measurements with its fixed reference position and generate correction data. This data then gets sent over to the moving one, which will use it to calculate its position with minimal errors, aka centimeter level precision. And luckily for me, according to my kit's user manual, this should all be easy to do, because it is all pre-configured and the modules already labeled as base and rover. So I mounted the rover board with antenna on top of my robot and used pretty much the same wiring as before. Then I had to adapt the code one last time to add an RTK status section, that basically tells us what RTK mode we're currently using, with number 4 being the best one. Now for the base station, I secured its antenna permanently at an elevated spot and simply had to power the baseboard using a power bank. After then placing the robot on my lawn and waiting for a couple of seconds, we apparently got RTK GPS going, meaning it was time to start the same test as before. Sadly though, at this point I realized the limitations of my robot, because it was not really capable of driving super precise, and its turning radius is just horrible. Thankfully though, I was still able to capture some usable landing points, which are way closer to the starting point than before when I was using normal GPS. The average tolerance seems to be around 20 cm, which is actually the tolerance I baked into the code, because the robot itself could never move precisely enough to hit a 1 cm target. Because yes, when repeating the standing still test from before, then you can see that the position really only drifts around 1 to 2 cm, which is an incredible improvement. So all in all, RTK GPS has become surprisingly easy to use nowadays. It works fantastically, but it is still pretty expensive. But overall, I'm happy to see that things turned out this way after my horrible results 11 years ago. With that being said, I hope you enjoyed this video and learned something new. If so, consider supporting this show through Patreon to keep it going. Don't forget to like, share, subscribe, and hit the notification bell. Stay creative, and I will see you next time!